Hello friends, so today we are going to solve the questions from modern physics. These questions are from the year 2024 and total we are going to solve 27 questions, and all these 27 questions are from mains. And this is part 1 for the year 2021. First question, it states that the radius of a nucleus of mass number 64 is 4.8 Fermi. Then the mass number of another nucleus having a radius of 4 Fermi is 1000 by x, where x is. So we are supposed to find out the value of x. So in this case, we are going to use the formula which we can call as a radius formula or nucleus radius formula. Nuclear radius formula, and it gives us that r is equal to r naught a raised power 1 by 3, where this r, it is the radius of the nucleus, radius of nucleus, r naught, or let us suppose first define a is our the mass number, and r naught is a constant which is same for all the nuclei. So r naught is our constant. So in this case, we are having two nuclei. Let us suppose these are our n1 and n2. So we can say nucleus 1 radius r1, that is given as 4.8 Fermi, and its mass number, let us suppose that a1 is our 64, and then we are having nucleus 2, suppose the radius is of r2, which is given as 4 Fermi, and a2 we are supposed to find out. We are simply going to take the ratio as per the formula. So we can write that of r1 upon r2 will be equal to r naught a1 whole raised power 1 by 3 r naught a2 whole raised power 1 by 3. R naught and r naught cancels out, so this comes as our a1 upon a2 whole raised power 1 by 3. And we are supposed to find out a2, therefore from here we can write that a1 upon a2 is equal to r1 upon r2 whole cube, and we can write that our a1 upon a2, r1 is our 4.8, r2 is 4. 4.8 divided by 4, this is our whole cube, and it will be coming as 1.2 whole cube, and a1 is given to us as 64. Okay, so we can say that our a2 will be equal to our 64 divided by 1.2 whole cube, and which will be giving us approximately as 37.037, and it is given that our A2 is 1000 upon x. So we can write that our A2, which is said to be given as 1000 upon x, and we found out this is equal to our 37.037. Therefore, we can say the value of x will be equal to 1000 upon 37.037, and this gives that our x is approximately equal to 27. So value of x is our 27. Next question. It states that in a nuclear fission process, a high mass nuclide A approximately 236 with a binding energy 7.6 mega electron volt per nucleon dissociated into middle class nuclides A approximately 118 having a binding energy of 8.6 mega electron volt per nucleon. The energy released in the process would be dash mega electron volt. So it means we have a high mass nuclei. Let us call that as our initial mass, or we can say our initial nuclei. So we can say we are given an initial nuclei, and let us denote it as AI, which is approximately equal to 236, and its binding energy also given to us. So we can say binding energy initial will be equal to 7.6 mega electron volt per nucleon. Then it dissociates into a middle class nuclei. Let us call that as final nucleus. Final nucleus, let us call this as AF, approximately given as 118, and corresponding binding energy final is our 8.6 mega electron volt per nucleon. And you can say that if we make a comparison between the initial and final, so we can clearly see that it is approximately our, you can say the value of is approximately twice. Okay. So let's find out the initial binding energy total. So we can say total initial binding energy, and let us call this as binding energy initial total. It will be equal to 7.6 multiplied by 236. So we get binding energy initial total will be equal to 1793.6 mega electron volt. Similarly, we are going to find out final binding energy total. So you can say total final binding energy, total final binding energy. Let us call this as binding energy final total, which will be equal to, it is given as 8.6 multiplied by 118. So we get binding energy final total will be equal to 209, sorry, not 209, but 2029.6 mega electron volt. Now we can find out the energy released, the difference between the binding energy. Therefore, we can write that energy released which is our delta E will be equal to binding energy final total minus binding energy initial total. We simply substitute the values, we get our delta E will be equal to 2029.6 minus 1793.6, which will be coming as 236 mega electron volt. So energy released is our 236. Next question. It states that the atomic mass of carbon is 12U and carbon 12 is 12 and that of carbon 13 is 13.003354. The required energy to remove a neutron from carbon 13 if mass of neutron is 1.008665U will be. So in this case, we are given that we have a carbon 13 and from this carbon 13 we are going to remove one neutron and that will be giving us carbon 12 plus 1 neutron. This is the basic, you can say, reaction which is going to take place. Now we can easily find out the mass difference, or we can say the mass defect. Mass difference, or we can say mass defect. So we can write our delta M will be equal to, we have our mass of carbon 12 plus mass of neutron minus mass of carbon 13, and we substitute the values. For carbon 12 it is exactly 12, mass of neutron is given as 1.008665 minus, and that of carbon 13 is given as 13.003354. So from here we get that the mass difference or mass defect will be approximately equal to 0.00, this comes as 5311U. And from here the mass defect we can just find out the energy released. So we can say energy released, or we can also call it as our binding energy of neutron. And that will be our E will be equal to mass defect multiplied by 931.5, which will be our 0.005311 multiplied by 931.5. So this gives us that the value of energy is approximately equal to 4.95 mega electron volt. This is our 4.95 mega electron volt. So option 3 is correct. 4.9, yeah, option 3 is correct. Is correct. Next question. It states that the explosive in a hydrogen bomb is a mixture of H2, H3 and lithium-6 in some condensed form. The chain reaction is given by, so we are given the reaction of our hydrogen bomb, and it is given the mass of lithium, mass of H2, mass of H4, as well as it is given that 1 AMU is our 9.31.5 mega electron volt. So question asked is, during the explosion, the energy released is approximately. Okay, so we have to find out what will be the energy released when the bomb is going to explode. So in this case, let us call this first part as first equation 1 and second as our equation 2. Now if we add equation 1 and 2, adding 1 and 2, this gives us lithium-6 plus we have this as our hydrogen-2 plus hydrogen-3 plus neutron-1, and on the right side we are going to get hydrogen-4 plus, sorry, not hydrogen but helium-4 plus hydrogen-3 plus helium-4 and plus neutron-1. In this case, this hydrogen-3 neutron cancel out, and finally we get this as our lithium-6 plus hydrogen-2 will be giving us, we have twice hydrogen, twice helium, so this will be giving us twice helium-4. Now we can just find out, because we have to find out the energy released, so we are going to find out the mass defect, and from there we are going to find out the energy. So we can just combine the formula and directly write it as energy released, that is our Q is equal to our delta M C square. And let us first of all find out this mass defect. This will be equal to, we have our mass of lithium plus mass of our lithium-6 rather, mass of our hydrogen-2 minus twice mass of helium-4 and multiply by C square, which is our 931.5, and it will be in mega electron volt. And we substitute the values, we get this as 6.01690 plus 2.01471 minus, this is our twice, and we have helium-4. Helium-4 is our 4.00388, and this whole term multiplied by 931.5. So this gives us that amount of energy released will be equal to 22.1 16 mega electron volt. So option number 4 is correct. 4 is correct. Next question. It states that in a nuclear fission reaction of an isotope of mass m, three identical, or rather three similar daughter nuclei of same mass are formed. The speed of a daughter nuclei in terms of mass defect delta m will be. So we are given that we have a mass capital M and it goes into fission and producing three daughter nuclei, and each daughter nuclei is having the same mass. So this will be m, m as well as m. So therefore we can write that our capital M will be equal to 3 times small m, or in the we can write this small m, this is 3, and we can say small m will be equal to capital M divided by 3. And mass defect is said to be delta m. Okay. So from the mass defect we can write that energy per nuclei, and in this case we can just assume that all the kinetic energy is coming from the mass defect. Okay. So let us say that all kinetic energy comes from mass defect. In this case we are just, it basically means we are going to ignore the binding energy. Okay. So we can write that our energy released from mass defect from mass defect, suppose that is given as E, so then this E will be equal to our delta m times c square. And like we said, that total energy released is assumed to be entirely kinetic and equally shared among all three daughter nuclei. Okay. So because all kinetic come from the mass defect and equally shared with all daughters. Therefore we can write that kinetic energy per nucleus let us suppose we write this as kinetic energy, and kinetic energy per nucleus will be equal to our 1 by 3 delta m c square. And we also can say that if all this daughter nuclei are moving with the velocity v, therefore kinetic energy associated with each daughter nucleus, can say kinetic energy of each daughter nucleus, that will be also equal to our half small m and v square. We know the relation between small m and capital M, so we can write this will be equal to over half capital M divided by 3, and we have this as v square. And both these expression, that is this equation 1 and equation 2, are the representation of the same, that is the kinetic energy of the daughter. Therefore, we can say equating equation 1 and 2, we get this as 1 by 3 delta m c square is equal to 1 by 2 m by 3 v square. Here 3 and 3 cancels out. Therefore, we can write that our velocity, that is v square, will be equal to, this will be our 2 delta m c square divided by capital M, or we can write our velocity v is equal to c square root, and we have this as twice delta m upon capital M. So we got the relationship of the velocity in terms of the mass defect, and option 3 is correct. Correct. Next question. It states that the mass number of a nucleus having radius equal to half of the radius of nucleus with the mass number 192 is. So once again, we are going to use the formula for the nucleus radius and start from there. So we can write empirical formula for nuclear radius. Empirical formula for nuclear radius, if that is represented as r, then this r will be equal to r naught a raised to power 1 by 3, where r naught is a constant, a is the our mass number, and this r naught constant is approximately equal to 1.2 Fermi, and that is universally for all the nuclei. And it says that the mass number having the radius equal to half that of the radius for mass number 192. Therefore, we can assume that the mass number of second nucleus, let us suppose is given as a prime, and the radius, its radius, it means radius of the second nucleus, radius of second nucleus, it is given as half the radius of nucleus for atomic number is equal to 192, mass number. And let us call the radius of the second nucleus as our r prime. So we can say our r prime will be equal to 1/2 multiplied by r, and from here we get our r prime upon r is equal to 1 by 2, and here we can just substitute their equations. So we can write that our r prime will be equal to a naught, not a naught but r naught, a prime 1 by 3 divided by r naught, and a 1 by 3 is equal to 1 by 2. Here r naught and r naught cancels out, and we get a prime. A we already know is our 192, will be equal to, this comes as 1 upon 8. So therefore our a prime will be equal to 192 divided by 8, which will be giving us 24. So option 1 is correct. Next question. It states that a nucleus has a mass number A1 and volume V1. Another nucleus has a mass number A2 and volume V2. The relation between mass number A1 and A2 is 4 times A1, then V2 by V1 is. And we can use a direct relationship between the volume as well as the mass number, because here we are going to find out a ratio, so we just can take it off as a proportionality. So we can say relation between nuclear volume and mass number. Nuclear volume V is proportional to our mass number, or we can also write it as volume directly proportional to cube of the radius and directly proportional to our mass number. And we just can take the ratio because there is a direct proportionality. So we can say our V2 upon V1 is equal to A2 upon A1. And we are already given that our A2 is 4 times A1 and this A1. So here A1 and A1 cancels out. So we get V2 upon V1 is equal to 4. So the answer is 4. Next question. It states that the minimum energy required by a hydrogen atom in the ground state to emit radiation in the Balmer series is nearly. So first of all, we have to remember that the Balmer series corresponds to transition that end at n is equal to 2. So we can say that Balmer series corresponds to transitions that end at n is equal to 2. So it means the electron must go from some level n that is greater than equal to 3 to 2. So from here we can say that n should be greater than or equal to 3, and finally it should come to end at n is equal to 2, and this is going to emit visible light. So in the question it is given that hydrogen atom is initially in the ground state. So first of all, from ground state it should absorb, and at least it should be coming to the minimum value, that n is equal to 3. Okay. Then it can come transition to level 2, which will be resulting in the Balmer series. So we can say, given that atom is in ground state, which basically means n is equal to 1 initially. Therefore, it must first absorb energy, because it has to be excited from n to 1, and the minimum level it should be our n to 3. So it must first absorb energy to get excited to a higher level, and that higher level minimum is n is equal to 3. So we can say at least n is equal to 3 before it can emit radiation. It can emit radiation. So it means first we are going to find out for the excitation needed. So we can say minimum excitation needed, which is our from n1 to n is equal to 3. Okay. And so from n1 to n3, which basically means, so when there will be a de-excitation, or we can say from n is equal to 3, it will be coming to n is equal to 2, is the lowest energy transition. Is the lowest energy transition. And please remember, this entire discussion is only for the Balmer series. So we can say is the lowest energy transition in Balmer series. So let's calculate the energy first from n to 1 to 3, then the other part also. Energy calculations. So first is from our n to 1 to n is equal to 3, and the energy difference, that is of delta E, will be equal to 13.6, and this will be over 1 square minus 1 upon 3 square, and this will be approximately coming as 12.09 electron volt. One second. Okay. So the answer we can approximate as, this can be approximately as 12.1. So option 4 is correct. Is correct. Next question. It states that a particular hydrogen-like ion emits radiation of frequency 2.92 into 10 to the power 15 Hz when it makes a transition from 3 to 1. The frequency in Hertz of radiation emitted in transition from 2 to 1 will be. So it given that from transition 3 to 1 the frequency is given, and we have to find out for 2 to 1. So we can write that from N3 to N1, suppose the frequency is of F31, that is given to us as 2.92 into 10 to the power 15 Hertz. And we have to find out when the transition is from N2 to N1, let us suppose that frequency is F21, whose value we are going to find out. We can just use the Rydberg formula. So you can say our Rydberg formula, but Rydberg formula we are going to write as a frequency. So you can say this will be equal to our frequency F is equal to R Z square 1 upon Nf square minus 1 upon Ni square, and we can divide into two parts according to our frequencies and take out their ratio. So we can say our F21 divided by F31 will be equal to R and Z will be common for both parts, and the only difference will be the value of N, initial as well as final. So this comes as 1 upon 1 square minus 1 upon 2 square, and 3 comes as 1 upon 3 square, 1 upon 1 square minus 1 upon 3 square. And this comes as numerator will be our 3 by 4 and denominator will be our 8 by 9. This can be written as, this will be our 3 by 4 multiplied by 9 by 8, which gives us 27 upon 32, and we are given F21 we are supposed to find out. So from here we can write that our F21 will be equal to 2732 multiplied by F31, whose value is known to us. Therefore we get our F21 is equal to 27, 32. F31 is our 2.29 into 10 raised to power 15, and this comes approximately as 2.46 into 10 raised to power 15 hertz. And so 2.46, option D is correct. 4 is correct. Four is correct. Next question. It states that the radius of a third stationary orbit of electron for Bohr's atom is capital R. The radius of fourth stationary orbit will be. So here we can just use the formula which states that the radius of the nth orbit. So we can write that radius of nth orbit that is of R of n will be equal to n square and R of 1. Here this R of 1 is radius of first orbit, or we can say Bohr radius. Radius of first orbit, or we can also call it as a Bohr radius, and here n is the principal quantum number. N is the principal quantum number, and we are given that the third radius is given as capital R. So we can say radius of third orbit that is our R of 3 is given as capital R, and in terms of the nth we can write this as capital R is equal to 3 whole square multiplied by R1, which comes as 9 times R1, and we need to find out the fourth orbit. So we can say radius of fourth orbit, let us suppose we give this as R of 4, and then this will be equal to 4 square multiplied by R1, which gives us 16 times R1. We can just take their ratio, and we can say that our R4 upon R3, R4 is our 16 R1, and our R3 is our one second, because we have to use this capital R, okay, because answer is in the capital R. So let me, therefore we can write that our R4 is equal to 16 times R1, and R1 we can write in terms of R as 16 multiplied by R by 9. and this gives us that R4 is equal to 16 upon 9 times R. So this is 16 upon 9 times R. Option 2 is correct. Next question. It states that if Rydberg constant is R, the longest wavelength of radiation in the Fission series will be alpha upon 7R, where alpha is. So with respect to Fission series, we have to find out what will be our alpha if the longest wavelength is represented as our alpha upon 7R. Okay. So here once again we have to keep in mind that for our Fission series, it corresponds to when the transition, or we can say the electron falls to n is equal to 3 from a higher energy level that is equal to n greater than 3. So Fission series corresponds to transition to n is equal to 3 from a higher level that is n is greater than 3, and we have to find out the longest wavelength, and the longest wavelength is rather we can say corresponds to the smallest energy transition or smallest transition. So we can say longest wavelength it corresponds to smallest energy transition. And smallest transition will be our from value of n 4 to n is equal to 3. So this will be giving us a wavelength. Let us suppose that wavelength is our lambda max. Now we can just use our, you can say, Rydberg formula. So we can say our Rydberg formula, which gives us 1 upon lambda is equal to our R 3 square minus 1 upon n square. And over here this lambda is our lambda max. Therefore we can write 1 upon lambda max is equal to our R 1 upon 3 square minus 1 upon 4 square. And from here we get our lambda max is equal to 144 upon 7R, but it is given as alpha upon 7R. So this is equal to alpha upon 7R. Therefore our alpha is equal to 144. Next question. It states that when a hydrogen atom going from N2 to N1 emits a photon, its recoil speed is x by 5 meter per second, where value of x is. So we are supposed to find out this value of x. Mass of hydrogen is given to us. So we can first of all find out the energy, and from there we can going to find out the momentum, and then we can just use our, you can say, the formula for our momentum, which is mass into velocity. So we start with our energy of the emitted photon. Energy of emitted photon when the transition is from n2 to n1. Let us suppose that energy is our E. So this E will be equal to 13.6, 1 upon 1 square minus 1 upon 2 square. And this comes as our 10.2 electron volt. And we can convert into the joules. 1.6 into 10 to the power minus 19 joules. So we get our energy E is equal to 1.632 into 10 to the power minus 18 joules. Now we can find out the momentum. Momentum of emitted photon which is our P is equal to E upon C, and so we get our P is equal to 1.632 into 10 to the power minus 18, 3 into 10 to the power 8. This gives us 5.44 into 10 to the power minus 27. And this will be equal to our mass into velocity. Is equal to mass into velocity. So we get that our velocity V will be equal to 5.44 into 10 to the power minus 27. Mass is our 1.6 into 10 to the power minus 27. So this 27 goes away. So we get the velocity is equal to 3.4 meter per second. But in the question it is given that recoil is x upon 5. So this is equal to over x upon 5. So from here we get our x is equal to 3.4 times 5, which gives that our x will be equal to 17. So the value of x is our 17. Next question. It states that hydrogen atom is bombarded with electrons accelerated through a potential difference of V, which causes excitation of hydrogen atoms. If the experiment is being formed at temperature is equal to 0 Kelvin, the minimum potential difference needed to observe any Balmer series lines in the emission spectra will be alpha upon 10, where alpha is. So we are supposed to find out what will be the value of alpha so that we are able to get any Balmer series line. Okay. And in order to observe any Balmer series line, the ending transition is our 2. So the starting transition will be greater than 2. It can be 3, 4 and something like that. Okay. So we can say that for Balmer series, the ending transition, we can say transition ends at n is equal to 2. Okay. And the minimum excited state of the hydrogen atom for the Balmer series is n is equal to 3. So we can write that electron must excite to at least n is equal to 3. Then only the Balmer series will be visible. Okay. Or we can write this as we start from n is equal to 3 and it ends at n is equal to 2. Okay. Then we are going to find out the Balmer series. But first of all, this hydrogen, or we can say the energy, it is going to start from ground level, that is n is equal to 1, and jump to n is equal to 3. Okay. So that energy we have to first of all find out. So we can say energy required to excite from n is equal to 1 to n is equal to 3. General formula we already know, that energy at nth level that is our E of n will be equal to minus 13.6 divided by n square electron volt. So we can find out our E of 1. E of 1 will be equal to our minus 13.6 electron volt, and E of 3 will be equal to minus 13.6 divided by 9, which comes as minus 1.511 electron volt. So therefore difference energy, that is delta E, will be equal to our E3 minus E1. E3 is minus 1.511 minus of minus 13.6. This comes as 12.089 electron volt. Now we come to the potential part, because it is being accelerated by a potential. So first of all, we are going to find out the corresponding minimum acceleration potential. So we can say corresponding minimum accelerating potential. So we can say that the energy required should be at least 12.089 electron volt. Okay. So it means we can write it as to provide at least 12.089 electron volt, an electron must be accelerated by a potential difference which is given to us as V, which will be equal to over delta E divided by E. And this we can write that our V delta E is our 12.089 electron volt. So this is 12.089 electron volt and divided by electron. So this E and E cancels out. This gives us 12.089 volts. But this is given to us as alpha upon 10. Therefore, value of alpha will be equal to 120.89. So we have alpha is 120.89. Next question. It states that the ratio of the magnitude of kinetic energy to the potential energy of the electron of an electron fifth in the excited state of the hydrogen atom is. So we are given that it is in the fifth excited state. So fifth excited state basically means value of n is equal to 6, because ground state is represented as value of n is equal to 1. So we can just use our Bohr energy model relationship. Based on this, we can find out the kinetic energy as well as the potential energy. So we can say Bohr model energy relations, and for we can say total energy, that is our for nth level, E of n is equal to minus 13.6 n square electron volt, and kinetic energy is nothing but the negative of our this total energy. So we can say our kinetic energy will be equal to plus 13.6 upon n square electron volt, and we can say our potential energy will be equal to minus, and we have this as 2.136 upon n square, sorry, not 2 point but 2 multiplied by minus 2 multiplied by 13.6 upon n square, because it is twice of energy E, electron volt. Now we are interested only in magnitude and find out the ratio. So we get kinetic energy oblique potential energy is equal to, we have this as 13.6 upon n square, and this is 2 into 13.6 upon n square. this 13.n square and n square cancels out, so we get this is equal to 1 by 2. The ratio is 1 by 2. Option 3 is correct. Correct. Next question. It states that electron of hydrogen atom on an excited state is having energy E of n, that is minus 0.85 electron volt. The maximum number of allowed transition to the lower energy level is. Okay. So here we are given for nth state, the energy is given as 0.85, and we also know the standard formula for nth state, and we can just equate them and get the value of n. Based on this we can find out the number of transitions. So we are given that energy of an excited state, that is given to us as E of n is equal to minus 0.85 electron volt. But for nth level, energy is, that is our standard formula, E of n is equal to minus 13.6 upon n square and electron volt. So we can just equate them. And we get this as minus 0.85 is equal to minus 13.6 upon n square, which gives us that our n square is equal to 13.6 upon 0.85. This gives us that the value of n is equal to 4. So the electron is at n is equal to 4 level. Electron is at n is equal to 4 level, and we can find out the transitions. We can say number of transitions we can use the standard formula also, or we can just find out how the jump is going to take place, like 4 from 3, then 4 to 2, 4 to 1, and then intermediate 4 to 2, 4 to 1 directly, something like that. Or we can say this will be equal to our n minus 1 divided by 2, which comes as 4 minus 1 divided by 2, which is equal to our 6. So number of transitions are our 6. Next question. It states that an electron revolving in the nth Bohr orbit has a magnetic moment mu of n. If mu of n is directly proportional to n raised to power x, then the value of x is. Okay. So we can use the standard formula, which gives us that the magnetic moment of Bohr model magnetic moment of electron, which is our mu of n, is given as E divided by 2m, and L of n. Here our L is our angular momentum of our nth orbit. E and m are the respectively charge as well as our mass. So we can say our L of n is our angular momentum of nth orbit in nth orbit. In nth orbit. Or from quantization, we can write that our L of n is equal to our n times quantized h. Therefore, we can write that our mu of n is equal to E upon 2m multiplied by n h quantized, and we can just make certain adjustment here. We can write this as n is equal to E h quantized divided by 2m. So this value is our constant value. Therefore, we can write from here that our mu of n is directly proportional to n. And in the question, we are given that our mu of n is directly proportional to n raised to power x. And we found out that our mu of n is equal to not equal to, but proportional to n raised to power 1. So if we make a comparison 1:1, from here we get that the value of x is equal to 1. So value of x is 1. Next question. It states that the mass defect in a particular reaction is 0.4 gram. The amount of energy liberated is 9 into 10 to the power 7 kilowatt hour when n is equal to. So we have to find out value of n, or basically we have to find out our energy, make a comparison with given energy value or formula. From there we can find out value of n. And in order to find out energy, we are going to use our mass defect. So we can say mass energy equivalence, or it is also sometimes called as a Einstein mass energy equivalence. Einstein's mass energy equivalence. Which gives us that energy E is equal to mass defect and C square. And mass defect is directly given to us 0.4 gram. So we can write this will be equal to 0.4 into 10 to the power minus 3 kg, and speed of light is our 3 into 10 to the power 8 whole square. So we get our energy is equal to, this will be our 3.6 into 10 to the power 13 joule. And we are given this is equal to n into, and we have to remember that the given unit is kilowatt hour. So we know that our 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joules. Therefore, our energy E will be equal to 3.6 into 10 to the power 13 divided by 3.6 into 10 to the power 6. This comes as 10 to the power 7 kilowatt hour, and it is given as n into 10 to the power 7. Therefore, we can write this as 1 into, so from here we get value of n is equal to 1. Next question. It states that which of the following nuclear fragments corresponding to a fission between a neutron and a uranium isotope 235 is correct. Okay, so this is directly based on the balancing our mass number and atomic number, and that we can just do directly also. So you can say balancing mass number and atomic number. And on the left side will be our fission is between neutron and uranium isotope. So we have uranium 23592 plus a neutron our 10, and that will be giving a product such that on the, suppose the total will be coming as 236 and here will be coming as 92. Okay. So we can just add them and we can see that this will be our 4, this will be over 3, this will be also 3, and this will be over 3. The rest of things will be following. 144 plus 4, that will be 148, and 89, and that will be our, so this won't add up, and so this is our 4437, so this won't also add up, and we are left with this will be 12 plus 3 16, and so on the denominator will be, this will be 92, so this might be one of the possibilities, and here also we are going to have 13 6, and here will be, and this will be our 4, 1 second, let me check thoroughly, 53 99, and we have this 3, and so we are going to get this as oh sorry, yeah, my mistake, I added it wrong. So this will be 5, not 6, so this cannot be correct, and we are left with this 144 89 and 3, so this comes as 6 and 3 and 2, and so option number 4 will be our correct. 144 BA 89 36 and plus 3. Yeah, so option 4 will be our correct option. Option 4 is correct. Next question. it states that the disintegration energy Q for the nuclear fission of uranium into our Ce, Z, R and N is given that their atomic masses as well as C square is given to us. So here we can just use our mass defect and find out the energy. So we can say our mass defect, which is our delta M, which is our mass for reactants, minus mass of the products, and reactant is our only uranium, so we get our this delta M will be equal to this, we are having 235.0439 minus we have our 139.9054 plus 93.9063 plus 1.0086. So this gives us that our mass defect delta M is 0.2236, and from here we can find out our energy released, which our Q is equal to delta M multiplied by C square, and we get Q is equal to 0.2236. C square is given to us as 3.1 mega electron volt, approximately 208. So we get this as 208. Next question. It states that if 3 helium nuclei combine to form a carbon nucleus, then the energy released in this reaction is dash into 10⁻⁻² mega electron volt. So in this case also we are going to use the mass defect, and the reaction that is given to us is that 3 helium is going to combine, giving us a carbon 12, and so we get our mass defect, which will be our delta M is equal to mass of reactant, that is 3 times mass of our helium 2 minus mass of carbon 12, and mass of carbon 12 is exactly 12. So we get this as our delta M is equal to 3 times 4.002603 minus 12. Exactly it is 12. This comes as approximately equal to 0.0078 AMU. Now we can find out the energy released. That is our Q, energy released, we will leave our Q is equal to delta M multiplied by 931 mega electron volt. So we substitute the value, we get Q is equal to our delta M is our 0.0078 multiplied by 931 mega electron volt. It is in 10⁻⁻². Okay, so we can write this will be coming as our 7.27 mega electron volt, or we can write this as 727 into 10 to the power minus 2 mega electron volt. So this comes as 727. Next question. It states that binding energy of a certain nucleus is 18 into 10 to the power 8 joules. How much difference between total mass of all the nucleons and nuclear mass of the given nucleus is? So we have to find out the difference, and we are given that our binding energy is given to us, and we know that our standard formula, that is our mass defect delta M, is equal to E upon C square, where this delta M is our mass defect, and we have to remember this is unit is our kg, and our this E is our binding energy, which is given to us as 18 into 10 to the power 8 joules, and C is the speed of the light, which we know is 3 into 10 to the power 8 meter per second. So we can find out that our delta M will be equal to 18 into 10 to the power 8 divided by 3 into 10 to the power 8, and this comes as our 2 into 10 to the power minus 8, 1 second, it is C square here, 2 into 10 to the power minus 8 kg, or we can write this as will be equal to, answer is in the milligram, so we can write this as microgram, 20 microgram. Option 2 is correct. Next question. It states that if M0 is the mass of isotope B12 and MP and Mn are the masses of proton and neutron, then the nuclear binding energy of the isotope is. So we are going to use mass defect, and based on this we can find out the binding energy, because we already know the relationship. Okay, mass defect is equal to binding energy divided by C square. And we are given a boron 12, and from here we can write that the number of protons that is our Z is our 5, and number of neutrons that is our N will be equal to 12 minus 5 is equal to 7. So therefore we can say our mass of nucleons let us call this as M nucleon, and we can write this as mass of our nucleon will be equal to 5 times mass of proton plus 7 times mass of our neutrons. Now we can easily find out our mass defect. Mass defect, that is a delta M. So we are having a total mass of 5 mp plus 7 mn, and the initial mass is given to us as our m naught. So this comes as minus m naught. So therefore you can say our binding energy that is our E is equal to delta M multiplied by C square. So we substitute value of delta M, we get this as our 5 times mp plus 7 times mn and minus m naught whole times C square. So the option is our 1 is correct. Next question. We are given in a hypothetical fission reaction, we are given X, and that is product gives Y and Z and 3 times R. The identity of emitted particle R is, we have to find out what will be our R, whether it is proton, electron, neutron or gamma radiations. So we can just use the balancing part. So we can say for our LHS, value of Z is equal to over 92, and for our RHS we have this as 56 plus 36 is giving us a 92 for RHS value of Z. And similarly for our LHS, value of A is equal to 236, and for our RHS, value of A will be equal to, we have 141 plus 92, which gives us 233. So it means there is a difference of 3 between the value of A. Z is same. So basically we can say that under this condition 3 neutrons are released. Neutrons are released. Or we can say our R is nothing but our neutron. So option 3 is correct. Next question. It states that the energy equivalent of 1 gram substance is, so this is directly based on our E is equal to mc square. So we can say our energy, which is our E is equal to m multiplied by c square, and this mass is given in gram, it should be in kg, so we can write this as -3, and this comes as our speed is our 3 into 10 to the power 8, and this is our joules, but it is in electron volt, so we can write this will be equal to our, sorry, it is square, so we get this as 10 to the power minus 3 multiplied by 9 into 10 to the power 16 multiplied by 6.241 into 10 to the power 18. Now this come in electron volt, so we get this energy will be equal to 56.169 into 10 to the power 31 electron volt, or in terms of mega electron volt we can write this will be equal to 5.6 into 10 to the power 26 mega electron volt. Or if we can multiply directly by 931.5, we can also get the same result. So we have option 4 is correct. Four is correct. Next question. We are given a star has 100% helium composition. It starts to convert 3 He4 into 1 C12 via triple alpha process as 4 He plus 4 He4 plus He4, giving us C12 plus energy. The mass of the star is 2 into 10 to the power 32 kg, and it generates energy at a rate of 5.808 into 10 to the power 30 watts. The rate of converting these He4, it means helium 4 to C12, is n into 10 to the power 42 per second. Then what is value of n? So we can just start from the reaction, and reaction states that our 3 helium is giving us C12 and of energy, and their respective masses are given to us. So first of all, let's find out the energy released by using the mass defect. So we can say energy released that is our Q is equal to delta M multiplied by C square, and delta M is our 3 times our helium. This is comes as 3 times 4.0026, and minus for carbon it is exactly 12, and whole multiply by 1 second. Okay. And first of all, let's find out delta M, then we can deal later on. So this is our delta M, and it will be coming as 0.0078 U, and we are going to convert this into our kg. So this comes as 0.0078 multiplied by 1.66 into 10 to the power minus 27, which will be giving us 1.29 into 10 to the power minus 29 kg. Now we can just find out our Q. So our Q will be equal to 1.29 10 to the power minus 29, 3 into 10 to the power 8 whole square, and this comes as 1.16 10 to the power minus 12 joules. And we are going to find out, because we are given the rate of conversion is given to us. So let's find out the number of helium nuclei in the, you can say, in the star. So you can say number of helium nuclei in star. Total mass of the star is given to us. Total mass of star, let us suppose that is a capital M. It is given as 2 into 10 to the power 32 kg. And mass of one helium nucleus, we can write that mass of one helium nucleus will be equal to, let us suppose, MHE. This will be equal to 4.0026 multiplied by 1.66 into 10 to the power minus 26. And we get this as mass of helium is equal to 6.6 into 10 to the power minus 27 kg. Now we can easily find out the number of helium nuclei. Number of helium nuclei, and He is equal to total mass of the star, and we have the mass of helium. So this is 6.6 into 10 to the power minus 27. This comes approximately as 3.01 into 10 to the power 58. Now we can find out the rate of consumption. Now in the reaction that is given, that 3 helium is giving to us 1 carbon plus energy released. Okay. So it means the rate of consumption of helium is, if rate of reaction is given as R, then the consumption of helium will be equal to 3R. So you can say each reaction consumes 3 helium. So you can say for rate of reaction is equal to R, then we can write rate of helium consumed. Rate of helium nuclei consumed will be equal to 3 times R. Now we are given the output power, and we can calculate this rate of reaction from the output power also. So we can say reaction rate that is our R will be equal to total power divided by released energy, that is our Q. released energy. So we get our R is equal to total power is our 1 point. It is given as 5.808. So we can write this as 5.808 into 10 is power 30, and our Q is our 1.16 into 10 is power minus 12. So this gives us 4.98 10 is power 42 reactions per second. And we know that we have to find the rate of converting of these means 3 helium to carbon. Therefore we can write that the rate of conversion of helium-4 to, this is about 3 helium, to carbon-12 will be equal to 3 times R, which is approximately equal to 15 into 10 is to power 42. But this is given to us as n into 10 is to power 42. This is given to us n into 10 is to power 42. Therefore, we can say value of n is equal to 15 approximately. So value of n is our 15. Next question. It states that a nucleus at rest disintegrates into 2 smaller nuclei with their masses in the ratio 2:1. After disintegration, they will move. We have to find the velocity as well direction. And so we are having a bigger nucleus, and it disintegrates into 2 nucleus, and suppose one is having a mass of m1 and other one is having a mass of m2. The ratio is given as m1 to m2 is equal to 2:1. Suppose this m1 is moving with velocity of v1 and m2 is moving with velocity of v2, and this bigger one, which is having a mass of capital M, its initial velocity is 0 because it is at rest. So we can use just conservation of momentum. Conservation of momentum. Initial momentum will be equal to 0. Let me write the formula. This becomes m times v is equal to m1 v1 plus m2 v2. Initial velocity is 0. Therefore, we can write this will be equal to 0 is equal to m1 v1 plus m2 v2. And we can write this as our m1 v1 is equal to minus of m2 v2. So at least from here, negative sign, it means direction will be opposite. So we are going to have opposite direction. So in terms of magnitude, we can just write it as m1 v1 is equal to m2 v2, and we are given m1 to m2 is equal to 2:1. So let us say that our m1 is equal to twice of m and m2 is equal to our m. So we simply substitute them. m1 comes our twice of m of v1 is equal to m times v2. So here m and m cancels out. Therefore we get our v1 upon v2 is equal to 1 upon 2, or we can say ratio is 1:2. So they move in opposite direction, but with the ratio of 1:2. So option 1 is correct. Next question. We are given that the energy released in the fusion of 2 kg of hydrogen deep in the sun is EH, and energy released in the fission of 2 kg of uranium is EU. The ratio EH and EU is approximately. We have to find out the ratio, and reaction is given to us. Fusion reaction is given to us, and the fission energy reaction released is also given to us. Per fission is given, and Na Avogadro's number is also given to us. So first of all, from the given reaction, we can understand that there will be 4 hydrogen and 2 electrons, and it will be giving a product of helium, 2 neutrinos and 6 gamma, and energy will be released. Okay. So we can say our reactants will be our 4 hydrogen and 2 electrons, and our products will be 1 helium, and we have 2 neutrinos and we have our 6 gamma and energy, and the value of energy is 26.7 mega electron volt. And let's calculate with respect to, because for fusion it is saying that 2 kg of hydrogen. Okay, let's calculate using the given amount. So we can say calculate number of particles in 2 kg. So first of all, let us say for hydrogen, and we know, or we can write that mass of one hydrogen atom, it can be written as 1 gram per mole, or approximately it can be written as 1 into 10 to the power minus 3 kg per mole. Therefore number of moles in 2 kg, number of moles in 2 kg, that is our N of H is equal to 2 divided by 1 into 10 to the power minus 3, giving us 2000 moles. Now we can easily find out number of hydrogen nuclei. Number of hydrogen nuclei, that is our capital N of H, is equal to N of H and multiply by Avogadro's number. It will be equal to our 2000 multiplied by 6.023 into 10 to the power 23. So we get number of hydrogen nuclei is approximately 1.2046 into 10 to the power 27. Similarly, we are going to solve for our, you can say, fusion reaction. Because in the fusion, each fusion consumes 4 hydrogen. So we are going to find out number of fusion reaction that is going to consume all these number of hydrogens. So you can say number of fusion reactions that will be equal to total number of hydrogen divided by 4. Okay, because each reaction consumes 4 hydrogen. We can write it here. Each fusion consumes 4 hydrogen. Therefore, it comes as 1.2046 into 10 to the power 27 divided by 4, which can be written as 3.0115 into 10 to the power 26. Now we can easily find out, because energy per fusion is given to us, that is our 26.7, and number of reactions, fusion reaction we know, so we can find out a total energy released. You can say total fusion energy released, which is given to us as E of H. So we can write that our E of H will be equal to, reactions are 3.0115 into 10 to the power 26. Energy released is our 26.7, and this is in mega electron volt. So we are going to convert into joules, that is 1.602 into 10 to the power minus 13. And we get that our energy EH is approximately equal to 1.29 into 10 to the power 15 joules. Now we find out similar way we are going to solve it for second one is our fission of our uranium. Okay, same calculation for our uranium now. Number of uranium atoms in 2 kg. Number of uranium atoms in 2 kg. And we start from the mole part. So we can say that mass of 1 mole of uranium 235 is approximately equal to 235 gram, or we can say 0.235 kg per mole. This is gram per mole. And number of moles in 2 kg uranium 235, let us suppose this is N of U is equal to 2 divided by 0.235, approximately will be equal to 8.51 moles. Now we can easily find out by our number of uranium nuclei. Number of uranium nuclei, that is our Nu, is equal to number of moles Nu multiplied by Avogadro's number. So we get our Nu is equal to 8.51 into 6.023 into 10 to the power 23. This gives us 5.13 into 10 to the power 24. Now we can find out the total energy in the fission. So we can say total fission energy, which is given as our EU. So this EU will be equal to total number, that is our 5.13 into 10 to the power 23, and energy released per fission is our 200 mega electron volt. So this becomes 200 into 1.602 into 10 to the power minus 13 joules. So we get this as our E of U will be approximately equal to 1.64 into 10 to the power 14 joules. And we are required to find out the ratio. So we get our EH EU is equal to 1.29 into 10 to the power 15, 1.64 into 10 to the power 14, approximately equal to 7.87. So approximately this is 7.62. Option 3 is correct. Is correct. So this completes all the 27 questions for the year 2024, and this was the only part 1. There are some remaining questions from the year 2024 which we will try to cover in part 2, and if required we can move into part 3 as well as part 4. So this completes part 1 for the year 2024, consisting of 27 questions. Thank you.